Okay, how is this working for sharing the screen? I actually don't have it in full screen mode so that I could see the chat. Does this look okay? Or otherwise I could put it into full screen and then I just won't see the chat. Okay, I can actually keep the chat on the side here. Does this look good now? Okay, it looks like it's the start time here. I guess we'll just wait 1 or 2 more minutes. Looks like we have about 30 participants. And I can share the slides following the talk. I'll put them on Campus Wire. Okay, looks like we're still getting a few more participants. Maybe I'll just wait a few more seconds and then we can get started. Okay, so it looks like we're at about 40 participants, so we'll get started. So um, thanks everyone for coming to this talk. So this is going to be a seminar. If you're not here as part of the AMMI program, this is part of a week-long course. And the seminar is going to be on neural text degeneration and also text generation. And we're going to focus on two different kind of streams that we'll go into called inconsistency and unlikelihood, which is based on some recent work that me as well as collaborators have done at NYU and as well as at Facebook AI Research. Okay, so recently, if you're in this course, it's a good time to be an NLP. So in terms of the research side, we see kind of growing number of papers every day, which means more ideas. If you're interested in, say, starting a startup one day, we also see some increase in investments in startups. Here on this website, you can see that there's over 400 different startup companies tracked by this website that are doing natural language processing. So there's been a recent sort of resurgence in this NLP. And this has led to some kind of interesting developments. So for those that are, if you remember this GPT-2 model that we use to sample these kind of realistic looking sentences, it turns out that right when this was released, the research group who actually made this model were sort of concerned that the model was so good at generating text that it could potentially be dangerous to release. And ultimately, they did release the model, but sort of the performance of these models is even raising kind of new concerns. And you can see that here, this is showing the number of parameters of language models. You can see that in particular, this language modeling problem, which we've discussed in the course, is specifically picking up a lot of interest. So here, Microsoft released the 17 billion parameter model. And maybe the surprising thing is that this paragraph here was actually generated by the language model itself. And you can see that the text here is pretty high quality. And all of this has happened in the last few years. But despite this progress, it turns out that these models aren't perfect. So in particular, they show something which we'll characterize as being called degeneration. And here's an example. So in this task, the language model is given this context. And the context ends with something like, the unicorns spoke perfect English. And then the task is to just continue generating text based on this context. And as you just actually learned about today, this is using beam search to generate. And you can see that after a while, the text that this model is generating actually becomes kind of degenerate. It just starts saying, of the world, to be a of the world, and so on, and just keeps repeating itself. And it turns out that this is actually this GPT-2 model. So this was this very powerful, large-scale language model, and it's possible to get this type of text from it. Now the question is, okay, is this maybe just one example? It turns out that if you take a similar language model based on the transformer and do the same sort of text completion task, it turns out that this repetition happens very frequently with certain decoding methods, which we'll discuss in this talk. And in particular, humans might repeat 4 grams about 1% of the time, whereas the model taken over all thousands of generations will have this repetition. About 40% of its completion will consist of repetition. So this is clearly not just a single example type thing. Something kind of major is consistently happening here. Okay, so now in this talk, I've just shown some examples. But the first part is we will discuss what we mean by this neural text degeneration. And part of that will be reviewing what we've seen in the course so far and trying to say something more precise about these odd behaviors that we're seeing with these language models is. And then the next part, we'll discuss a recent paper which kind of deals with a theoretical aspect that we know about this text generation, degeneration. And then finally, based on kind of what we know, we'll talk about some ways of preventing this degeneration. And throughout the talk, I would encourage you to think of potentially other ways, because this is a very sort of new and ongoing problem, and it's interesting to think about what can be done in the future as well. Okay, so as background, we're going to be dealing with this problem of neural sequence modeling. And so as you've seen in the course, this is a very general problem where the first step is to estimate some model, and the model is conditioned on some context. So in this case, we're showing a Japanese sentence. In the case that you saw on the previous slide, it was some prefix, right? And then the model is modeling some distribution over sequences. In this case shown here, it's modeling the English translation. And on the previous slide, it was modeling the sort of continuation of the sentence. Then given a trained model, we actually want to obtain sequences from the model. Looks like there's, for some reason, some kind of drawing on my screen. I'm not sure if people are seeing that as well. It looks like someone is annotating the slide. I don't think that was me, so if it's possible for you to delete it, please delete your annotation. Okay, I'll just continue though. Yeah, so whoever drew this line, if you wouldn't mind, please delete that. Okay, so then the second step is, given one of these trained models, we actually want to obtain sequences from it. And we're going to do that with a decoding algorithm, which we actually, if you're here for the course, we just talked about today. And so we're going to denote that using this F symbol. And a decoding algorithm, when you think about it, what it does is it takes in a model, and then it'll take in some input, so a context, and then it produces some sequence. Okay, so that's the general setup. And now how do we actually go about solving this problem typically? Well, you could kind of break it down to three things: model, learning, and inference. Okay, so on the model side, this kind of standard approach is to use these autoregressive neural sequence models, which, as we've seen, means that you're modeling this distribution and decomposing it into these conditional distributions. And then each conditional distribution is going to be parameterized using a neural network. And so the kind of current standard ways, which are also the ones that you saw in the course, are to use something like a recurrent network or to use something like a transformer. Okay, and now maybe the new thing, the good way of thinking about what these models are doing for this talk is to think about the space of all sequences, right? So this here will represent any possible sequence that you can generate. And you could think of this model as defining some distribution over these sequences, right? So here we see a kind of probable sequence according to the model, which is, how are you? And here, this would be something where the model would actually give 0 probability. Okay, so then once we specified some model, this kind of standard way of learning is to use this maximum likelihood estimation, where we have some data set, and then we want to maximize this quantity here, which is the log likelihood, or the probability of this data set. And then finally, as far as inference goes, once we've trained the model, now we want to obtain some sequence from it, given some context. And as we saw earlier today, this is a difficult problem because if we're searching through the space of all possible sequences, that's very large. And so in practice, what we do is we use some approximate decoding algorithm. And here's this notation again. And that could be something like greedy, beam, or some sampling type approach. Okay, so that's a review of the kind of conventional way of doing this model learning and inference. And the interesting thing that you could think about is that actually when we use a decoding algorithm, what it's doing is actually defining a new distribution over these sequences. So let's think about this for a second, that if you use something like greedy decoding, there might be some sequence which you just never obtain with greedy decoding. And so that might be over here. Whereas there might be some collection, or there is some collection of sequences that are probable under, say, greedy decoding, and more probable under greedy decoding than they are according to the model. And what we'll see later in this talk is actually that there's this discrepancy, that the decoding distribution might not even overlap in certain parts with the model distribution. And this might actually lead to some issues, as we'll see later in the talk. Okay, so then just as a quick review of these decoding algorithms, for greedy search, we're doing this maximization at each time step and just taking the most likely token. For beam search, this doesn't contain all of the details, but just as a quick review, it's sort of a generalization where we're maintaining k high-scoring prefixes and expanding each prefix by appending a vocabulary item or token at each time step. And we just saw more details about these earlier today. In terms of sampling algorithms, the simplest is to sample from the model's distribution at each step. Okay, and so here this is showing at one step of generation, the model's distribution, and we're going to just sample from it. We also saw two different variants. So in top K sampling, you're going to take the original model distribution and then just restrict sampling to the top K most probable tokens. Okay? And if a token is not in the top K most probable, then it'll actually get a 0 probability of being sampled. Okay, so that's top K sampling. Similarly, we could do something which we again saw, which you could call top P, or this nucleus sampling, where we're going to restrict certain tokens based on their probabilities. So here with this example of nucleus 0.8, we're going to essentially collect tokens until the sum is equal to 0.8 and discard the rest. So in this case, we'll discard these two low probability tokens that have 0.1 each. And then we'll sample from this actual distribution here. Okay, and so now with the setup, we can at least say something a bit more precise, which is that this text generation is a situation where language are producing text which differs from the true distribution. And in particular, it's when we're using these decoding, saying that induced distribution from the decoding algorithm here in red is differing from this true distribution here. And for example, this decoding algorithm might be putting some probability on some degenerate sequence like this, whereas the true distribution, you'd never see that in the actual distribution. So, now, what does that actually lead to in practice? Well, we could kind of break it down into three different symptoms. So one is this, where the model just enters into some kind of repetition loop and starts saying the same thing over and over. And actually, if you were paying attention in the dialogue modeling lab today, you actually saw that dialogue model repeating how it liked to hike and liked to hike and liked to hike. So you actually, you may have not noticed it, but you actually saw this repetition today. A kind of similar phenomenon, but I'll consider it as a separate phenomenon, is that sometimes when you produce sequences from these models, they actually will never end. They'll never terminate, which means that the model just never produces this end of sentence token. So here's an example again with this GPT-2, and it's fine-tuned on this data set. And when you generate these completions from this text completion task, it turns out that the true data here in blue, the sequences in the data set are, of course, going to terminate. They have some ending point. Whereas the model, here we're using a maximum length of 500. The model often just keeps generating forever, right? And so a lot of the times these infinite generations are going to be repetitions, but we also do see repetitions in shorter sentences. So we could kind of view those two things as related, but maybe two different symptoms. And the third that we actually won't go into much in this talk is this logical contradiction. So here you see a dialogue model, again, trained with the maximum likelihood. And here it has a persona which says it has 2 cats. And here the model says something sensible, which is that it has 2 cats. And so this is a dialogue that, again, that the model is having with a human. The human responds. And now the model, given this context, says something contradictory. It now says it doesn't have any pets. So although the language itself looks sort of reasonable, right? Like this is a well-formed sentence, the logic of the sentence is incorrect and contradictory. And it turns out that the same thing happens in a non-dialogue setting. So with GPT-2, you could actually try this yourself on one of these online things like talktotransformer.com. Here we're generating I love basketball. And then it says I really dislike. And if you look at the top ranked token for the next time step, it's now saying I really dislike basketball. And you can see how if you were to use greedy decoding, it would then contradict itself there. Okay, so these are sort of 3 different ways of characterizing this text generation. And now we're going to actually focus on this non-termination. So this is part of a recent paper that we've worked on here at NYU, along with the collaborators shown here. I think I saw Ilya's on this call, and Cho and the others might have joined as well. And this is called consistency of a recurrent language model with respect to incomplete decoding. So after the next part, hopefully you'll understand what these words mean. Okay, so again, so in this project, we're going to focus on this issue where we see these completions which appear to be infinite length. So here's this example again, where the model starts generating. In this case, it's also repeating itself. But it turns out that this generation just keeps on going forever, and it never is generating this end of sequence token. And here's the same plot that you saw before, which shows that it's occurring quite often. So the first question is, can we kind of more formally describe what's happening here and analyze it? And then maybe based on that analysis, can we somehow fix this issue? And so in order to formally analyze, we have to clearly define what type of model we're using. So this is kind of more formal, but it should be a pretty familiar definition of a recurrent language model, where we have this familiar softmax distribution here. The model's having some conditional distribution over the next token. And here, again, you could think of this model defining a distribution over these output sequences, which is shown here. And the task that we're going to be concerned with is the one that we've been seeing in these examples, which is this text completion. So here, given this context, I have a pet, one possible output sequence might be a dog whose name is Spot, right? So I have a pet dog whose name is Spot. Okay, and now one definition that we consider here is to actually think about these different decoding algorithms that we've talked about. And in general, they're kind of doing something common. And we're going to call this incomplete decoding. So what is incomplete decoding? Incomplete decoding says that at a given time step, the decoding algorithm is going to actually discard some tokens, in the sense that the decoding algorithm is going to put 0 probability on some strict subset of tokens. That's this VT prime. And so an example is with this top K decoding. So here we start with this distribution, and then top K decoding is going to actually put 0 probability on these tokens. And this is just a formal definition for this general thing that's happening when you think about it with greedy decoding, with beam search, top K sampling, and with nucleus sampling. And so we're going to call any algorithm that has a behavior similar. And then if you remember from the title of the paper, it had this word consistency. And so consistency here is going to be the way that we're going to formalize this idea of infinite sequences. Okay, so in particular, you say that a model is consistent in infinite sequence. So the model will assign a probability of 0 to every infinite sequence. That's what this is saying here. If that's not the case, we call the model inconsistent. So just loosely speaking, you can think of consistency as meaning that the model is only putting probability mass on finite sequences, which are shown here in the, or not even loosely speaking, that is the definition, on finite sequences, which are shown here in this darker blue. And it's putting 0 probability on an infinite sequence in this region. If the model was inconsistent, it would look something like this. It would have some probability mass placed on these infinite sequences as well. Okay, so that's a definition. And now the first question to ask is the model consistent? So just to make sure we're again on the same page, we're trying to figure out why are we seeing these infinite sequences generated from the model. And the first natural question might be, does our model look something like this? Is it somehow through this learning process putting probability mass on these infinite length sequences? It turns out that the model is consistent. So that means that the model is actually only putting mass on finite sequences. And it turns out that you could formally show that the language model is consistent as long as its hidden state is uniformly bounded. And some things that you've seen in the course will guarantee that this is true. So if you use, for example, the tangent activation function, or if you use layer normalization, which we saw in the transformers, then your model will be consistent. And so again, kind of visually, it looks like this, where our model is actually putting 0 probability onto these infinite length sequences. And now this is kind of surprising, maybe at first, that we're somehow getting these sequences, but our model is saying that those sequences have a probability of 0. But there's still hope. We also can consider the decoding algorithm. So if you remember, the model paired with some decoding algorithm is going to define some different sequence distribution. So now the question is that sequence distribution consistent? And it turns out that the induced distribution, when you pair the model with some decoding algorithm, is not consistent. And more specifically, when you pair the model with any incomplete decoding algorithm. So if you remember from a couple slides back, we saw that things like greedy search, things like top K, they're known as these incomplete decoding algorithms. And it turns out that when you decode using one of these algorithms, then it's possible to decode an infinite length sequence. And if we remember, since our model is consistent, it's kind of this paradox that the sequence actually has 0 probability according to the model, but we're still able to decode them. So the situation looks something like is shown here, where this distribution that we get from using the decoding algorithm is actually going to allow us to obtain these infinite length sequences. Okay, so if you're able to kind of follow the logic there, at least now what we've done is we've more formally started to understand what is this symptom that we've been seeing. And in particular, we saw that there's this discrepancy between the model and between the decoding algorithm. And that, in particular, these incomplete decoding algorithms are part of the issue. But still, sort of what, this is just a theorem. What's actually going on? Can we get some kind of intuition? Well, the intuition is that when you use one of these incomplete decoding algorithms, it's possible that the algorithm will actually discard this end of sentence token, right? So this can just happen if the model always ranks this end of sentence at the bottom. And you can imagine that if end of sentence is discarded at every time step by the decoding algorithm, then you're never going to terminate the sequence. Okay, so the model is ranking end of sentence outside of this kind of window, and it's being discarded, and that's happening at every time step. And it turns out that this intuition is exactly how you can formally prove the theorem that we saw before. Let me see. Okay. And it also turns out that this intuition is useful for thinking about how we might fix this problem. Okay, so in summary, we saw that it's possible to decode infinite sequences due to this mismatch between the model and the decoding distribution. And now we could think about how we might fix it. And for thinking about how to fix it, we could separate it into model, learning, and inference, like we did before when introducing sequence modeling. And as a first step, we could think about how can we design some different decoding algorithm to prevent this. And using the intuition that we saw before, we can kind of see that a sequence will always terminate as long as you ensure somehow that end of sentence is eventually sampled. And how we're going to do that here, it's a kind of simple approach. We're going to modify top K sampling, where we're not only going to consider the top K next tokens, but we're also going to consider at every time step end of sequence. So in this way, this decoding algorithm, which we'll call consistent top K sampling, will never discard EOS, end of sentence or sequence, just by definition. Okay, and then if you want, you can write down again formally that this will result in a consistent sequence distribution. We can use the same idea with nucleus sampling, where again, we explicitly include this end of sequence into the set of tokens being considered at each time step. And again, this means that the algorithm will eventually sample this end of sentence because it doesn't have a zero probability. And I think hopefully you could see that these are maybe simple approaches where we're explicitly including this end of sentence. But now with this kind of formal understanding of what's going on, you might be able to think of some other alternative approaches for addressing this through an inference method. Okay, and now another approach we could take is to modify the model. Right, so we have this vanilla recurrent language model. And can we somehow get this model to ensure that end of sentence is eventually top ranked? Because if end of sequence is eventually top ranked, then any of these incomplete decoding algorithms won't discard it, and it'll eventually be selected. And so what we propose here is called the self-terminating recurrent language model. And it's kind of a lot to see this all at once. On the next slide, I'll actually talk about the intuition of what this is doing. But you can see that what this is doing is modifying this conditional distribution, okay? And it's actually going to do something separate for the end of sequence position. When the token is not end of sequence, so for the rest of the distribution, this is just a softmax here. And it's reweighted by the kind of remaining probability mass here, alpha. And then alpha is defined in this manner. And it's sort of this recursive definition, where alpha is defined by multiplying some number here, which is less than 1, times 1 minus the previous end of sentence probability. Okay, so that's the kind of specification. I think if I was seeing this for the first time, maybe I wouldn't immediately see what's the key idea. The key idea is that when you use this parameterization, the end of sentence probability behaves like this. Okay, so at the first time step, sorry, as the number of time steps increases, the end of sentence probability is going to be 1 minus the product of numbers that are less than 1. Okay, so over time, this product is going to go towards 0, which means that the end of sentence probability is going to go towards 1. Another way of saying it is that the end of sequence probability is guaranteed when you use this model to increase monotonically over time. And so eventually, end of sequence will be top ranked and it'll be selected even when you're using one of these incomplete decoding algorithms. Okay, so those were two different methods from the model and inference perspectives. Now let's take a look at some experiments. So the first question to ask is, with these models that we've defined here in the paper, does this inconsistency or non-termination or generating infinite length sequences, does it actually happen in practice? So what we did is we used different decoding algorithms and then decoded many different sequences. And we called the sequence infinite if it didn't stop within 1,500 steps. Okay? And the maximum length in the data set was around 100. So this was 1,500 steps never occurred in the data. And you could see here that when you sample from the model, it always terminates. And when you think about what that means, this is actually saying that our model, this is a way of seeing empirically that the model itself is consistent. Because here we're just sampling directly from the model's distribution, And that distribution does not have any probability mass on infinite length sequences. On the other hand, when you use these different incomplete decoding methods, you'll see varying levels of non-termination. And in all cases, you'll see at least some sequences not terminating. You can see that the problem is kind of complicated because non-termination varies based on the type of model you use, and then it'll also vary on these based on these hyperparameters. The hyperparameters are actually kind of intuitive, that as the size of this window grows that the incomplete algorithm is considering, the chance of EOS being selected will increase. So this is on these models from the paper on Wikitext too. Maybe surprisingly, we actually saw on the earlier slide that with the very large scale GPT-2 model, the non-termination was actually happening more frequently, and that was showing with greedy search. So it looks like this does occur in practice, not just in the theory. This is showing if we use one of these consistent sampling methods, the termination rate compared to the inconsistent version. Right, so here's top K vanilla version versus the consistent version. And you can see that, maybe not surprisingly, since we're including end of sentence every time, it's going to terminate in all cases. What does this look like in terms of generation? Here we're using this consistent nucleus sampling and comparing it with normal nucleus sampling. And so again, the task is given some prefix, generate some completion. And you can kind of separate it into three different cases. In the first case, both the normal nucleus and the consistent nucleus terminate. And in those two cases, they both look kind of reasonable. In the second case, you could see that nucleus sampling is going to continue on towards infinity. And in this data set, there's a lot of these unknown tokens, and it's also a smaller data set and smaller models. So the quality of the generation might not look as convincing as other things we've seen, but hopefully you could see the ideas that are coming across here. And the idea here is that with nucleus, it's going to infinity, but now that we've prevented the inconsistency, we maybe get something reasonable from the model. In the third example, we could see that nucleus, again, is going to infinity, but the consistent model is stopping, but maybe still starting to repeat itself. So that's maybe showing that you can sometimes consider the repetition and non-termination separately. In terms of the self-terminating recurrent language model, you could see that the non-termination rate, okay, so the original model is going to be shown with the circle, RNN and LSTM, and the self-terminating versions are here. So you can see that the perplexity slightly gets worse. We are modifying the conditional distribution, but the non-termination rate is going to 0. It turns out that there is a hyperparameter, epsilon, and if that's incorrectly set, then it's still going to not terminate. Oops. And again, we could see more generations here. Similar, we have these three different situations. So both are good. One of them improves due to termination. And the self-terminating version terminates, but it maybe still does this kind of repetition. So the problem is maybe not completely solved. But we do see some improvement, and at least we understand kind of what's going on here. And let's see, anything else with that? Oh, okay, and this is again using just greedy decoding for both. So this is showing that you can still use an incomplete decoding method when you modify the model in this way. Okay, so far we saw that this text generation is characterized by non-termination, repetition, and contradictions. And the common models and decoding algorithms can yield infinite sequences when they rank EOS low. And we've talked about two different methods. So now we're going to talk about this repetition issue and a learning method for preventing the repetition. And that's going to be called unlikelihood training. So here are the collaborators on this work. And this is going to be presented soon at iClear 2020. Okay, and so in this work, we look at this learning aspect. And we ask the question, is maximum likelihood the reason or a cause for this text degeneration? It turns out that that's kind of a difficult problem. We'd all like to know exactly why this is occurring. And so in this work, we kind of took a first step, which says, can we design a different learning objective that doesn't result in this degeneration? And then as even more of a kind of simplification, maybe we have to specify exactly what kind of behavior we want to prevent. So specifically, we'll be looking to prevent this repetition. Okay, so as a review, the standard, or what we'll be kind of looking to improve upon here is this maximum likelihood estimation. And when you think about what it's doing, given some ground truth sequence, at each time step, we're going to increase the probability of the ground truth next token. So in this case, hello, how are? And the ground truth next token is going to be you. And so you could think about two different potential downsides with this approach. The first downside is that although all of these tokens will have their probabilities decreased since we're using softmax, we're kind of not explicitly decreasing different tokens to different degrees, right? Our kind of supervision is only on increasing this ground truth token. Another potential issue is that all of the training in this case is done using this ground sequence. Whereas, as we've kind of talked about during this entire presentation, when we actually go to generate sequences, we're using a decoding algorithm. So it might be good to think about how we could train using decoded sequences. Of course, that's difficult because we don't know, for example, what the ground truth token is in that case. You might be we're going to focus on this repetition, and we're going to measure it using this 4-gram repetition metric. And again, the task is going to be this text completion, and we're using a relatively large-scale transformer model. Okay, and so the proposal in this work is to modify the training procedure, and it's called unlikelihood estimation, or unlikelihood training. And unlikelihood training takes the original maximum likelihood loss and adds an additional term here, which we'll call the unlikelihood loss. Now, the unlikelihood loss at each time step, so this is showing one time step, is going to have some tokens which we'll call negative candidates. And I'll talk about how to get those in a second. And the unlikelihood loss is going to take each negative candidate, and it's going to decrease or encourage the model to decrease the probability of that negative candidate token. So that's what this log 1 minus p loss is doing here. And now this is, again, just training with some ground truth sequence. And we're applying this loss to a conditional distribution. So we call this a kind of token level loss. And in this case, what we found, we tried different alternatives. We found that setting the negative candidates to be the preceding tokens was kind of an effective way of reducing this repetition. And so this is visualized below, where now our loss function is again increasing the probability of the ground truth token, but now we're explicitly decreasing the probability of these previous tokens. And that's only if the ground truth isn't in the previous token. That's what this is doing here. And when you think about it, that's actually exactly what repetition is. Repetition is producing a token which you produced in the past. And so here we're decreasing the probability of doing that. Now, we talked about two different downsides with maximum likelihood. The second downside was that it never trains on actual decoded sequences. So to address that, we could think about this sequence level version of unlikelihood. So in this case, we again have a ground truth input and ground truth output, and we just use maximum likelihood loss on that. But now we additionally decode some sequence using some decoding algorithm, and then apply an unlikelihood loss to that decoded sequence. In this case, the question again is, how do we define these candidates? And in this case, what we're going to think about is, given some decoded sequence, like is shown here, we're going to kind of put these penalties on different tokens. So the candidate is just going to be defined as the token itself or just nothing. And so here we're seeing just choosing random candidates. So here we decoded a sequence again, and then randomly you're going to say decrease the probability of these tokens. Another thing you can do is to explicitly kind of go after this repetition problem. And so here you're going to explicitly look at what are the tokens which participate in repeats, and apply this unlikelihood loss to those repeats. And again, this is what this looks like. So if you consider just this time step, crash, what it means is that we have some loss, which says 1 minus the probability of generating this negative token here, crash. And it'll look something like this. Okay, so that's unlikelihood. That's the method. How does it perform? Okay, so here is showing using both the token level and sequence level unlikelihood, and using these repetition candidates. And you could see here that when we complete this prefix, which starts with including French, Spanish, and so on, the maximum likelihood baseline just begins to repeat a bunch of language names over and over. And it gets about 74 for this 4-gram repetition metric, 74%. When you use this unlikelihood, the text is much different. So here you can see that it's actually having some sort of fluent text about singing and about some relationship between the protagonist and her lover, and going on about the singing. And to give you an idea of this repetition metric, in this case, this is about 6%. Here's the example that we've seen over and over again in this presentation. And you can see that in this case, using this unlikelihood training completely changed the generation quality. Instead of this repetition, now you see some kind of interesting scenario about this general. And I actually haven't read this in a while. So, okay, the order to abandon ship was given by Admiral Beatty, who ordered the remaining 2 battlecruisers to turn away. So much different. If we just look quantitatively, what's going on, this MLE model, again, is going to have about 44% repetition with greedy, about 50% with beam. And maybe an interesting thing is that just using these random candidates, if you remember from the previous slide, you can substantially reduce the number of repetitions. That's kind of interesting because using random candidates, we never kind of hard code in the notion of repetition. And so this is potentially something interesting to think about for maybe some future method where we want to remove this kind of hard coding of the repetition. And then here we see that using the repetition candidates, we get very low repetition. And with beam search, now, I mean, beam search was previously unusable, about repeating itself 50% of the time. And now we can see that beam search is actually approaching the human repetition rate of around less than 1%. Perplexity does, well, it actually decreased in this case. It does slightly increase, but what we'll see on the next slide is that this doesn't lead to a meaningful change in the quality that you see. Okay, so here we're actually seeing human evaluation, where different humans will look at the text that these models generate and evaluate, is this model better than this model here? And according to humans that were reading these, this unlikelihood method actually was able to generate better text than maximum likelihood with greedy search, but then also with this nucleus sampling and something else that explicitly blocks out repeats called beam blocking. So you can see that what's maybe not clear from these metrics is, is the actual quality of the generation improving? And at least according to both these crowd workers and these experts, the quality was improved. Okay, so I have about 5 minutes left. So I just wanted to comment a few things on trying to get some understanding of why this might work. And we don't completely have the answer, so these will just hopefully give some intuitions. One is to actually look at the gradient that's being computed. When we look at the gradient, it looks something like this, where we have the ground truth next token as a one-hot vector, and then we have this kind of mask for the probability, and it looks like this. Kind of stepping through this, I probably won't have time, but if you look at what's happening here, in the case of the negative candidate index, so here, it turns out that the gradient will always be negative, which kind of makes sense. We want to decrease the probability of one of these negative candidates. Conversely, for the ground truth next token, it always has a positive gradient. Then the interesting thing is that for all other tokens, the behavior actually differs. And in particular, when the model is assigning a lot of probability to a negative candidate, it will actually increase all of the other tokens along with the ground truth token. So it's kind of intuitively, I see this as it's putting a lot of effort to moving things away from this negative token. But then once the negative token has sufficiently low probability, the gradient actually switches to negative for these others, and it looks, it has the same, at least direction behavior as maximum likelihood. This again is just going to be a rough intuition, it's nothing formal, but possibly comparing this unlikelihood with other methods might either lead to insight on why this works, or it could lead to alternative methods in the future. And so here, I just wanted to compare it to this noise contrastive estimation, which is commonly used to train these energy-based models. And the noise contrastive estimation has two different terms. It has this positive term, where you're sampling some positive data. And then it also has this negative term, where you're sampling some negative data, and you see this log of 1 minus h of the negative data. Now, in the case of noise contrastive estimation, this h takes this form here, and that allows you to kind of interpret it as this discriminating between the positive and the negative noise. And this method actually has formal guarantees for the convergence. Now, we're not going to claim that it's an exact match, but you might think about this as being something roughly similar to this, in the sense that we have this positive distribution and negative distribution. And in particular, if we think about these random candidates, what we're doing is, if we just think about one time step, we're taking a time step and using the ground truth, we're increasing its probability. So this would be a ground truth next token. And for a negative candidate, we're kind of sampling a time step randomly, and then we're decreasing the probability for that conditional distribution. Okay, so you have this positive increase and this negative increase. But I think making these comparisons, there's still more work to be done, and it could be interesting to think about in the future. And lastly, as a follow-up, we actually applied this to this dialogue problem. So instead of the text completions, you might wonder if this unlikelihood training actually leads to improvement on a more real-world task like dialogue. So for that, I won't have time to go into the details here, but you could check out this paper, Making Inconsistent Dialogue Unlikely with Unlikelihood Training. And there, we actually looked into things beyond the repetition. So in particular, we also looked into these logical contradictions, as well as the frequency of different tokens that were happening, and kind of used this unlikelihood training in different ways for addressing those issues. Okay, so as a recap, we discussed this issue, which we call text degeneration. And you could kind of characterize it by three different things. Having these non-terminating sequences, having repetition, and having these logical contradictions. Throughout the talk, we saw that new models, new inference methods, and new learning methods can address these issues. But I want to emphasize that this isn't all solved. So I think we should use these findings that we have as a starting point and start to think about, okay, how can we develop even better inference methods with guarantees? How can we develop learning methods that maybe have fewer and fewer restrictions and also have more formal guarantees? And potentially, how can we think about different models? Okay, so with that, I want to thank you. And in this case, this repetition is good because it says very much for infinity. So thanks. I guess we're out of time, but we could take maybe questions or just discuss more in Campus Wire.
All right, thanks for the nice talk, Sean. So we are going to have a dinner break in Kigali, and it's going to be lunch break for us in New York City, and then just break for you all in Accra. So it's going to be an hour break, and then we'll be back for the very last lab session of the course at 7 p.m. in Kigali, 5 p.m. in Accra, and 1 p.m. in New York City. And then Sean is going to tell us about BERT and how we can use BERT to do various things, including generation and also to do factoidal question answering. And just to clarify what I said earlier, final exam is going to be online and will be done via Gradescope. It is going to be available from tomorrow, and then you're going to have 1 full week to complete it. And it's all open book. You can check the internet, you can read the books, you can talk with your friends if you want, and then answer those questions as well as possible. And then you just have to submit it by Thursday next week, not tomorrow. Then have a nice dinner, and then I'll see you all, and we'll see you all in an hour then. Thanks, Sean.
Okay, thanks everyone.